All right, we're going live on our Ham Radio Workbench live stream. So, hello, Mike. How are you?
Hello. Hola. Great. From the
Good to
Great
see you.
White
Hey,
North. I'm the only Canadian tonight.
you are. We're two down. You have to represent.
Finally, we're not outnumbered, George.
Hey, Mark, how are you?
I'm doing well. How are you?
I'm doing very good. Actually, it's cold. It's colder than usual. So, uh, here I know you Canadians are just laughing because it's gotten down to 50 here,
I
and
know.
so we're all freezing. What's it
Yeah.
like up there, Mike? Is it
Oh,
breaking
I'm
zero?
sorry. So just so you know, I've got three screens going, and
Yeah.
the YouTube one's lagging. So I'll be answering questions, by the way, in the YouTube stream. So I might be a little delayed, but they'll keep me honest. So today, we've had rain and fog and freezing rain for the last couple of days, on and off in different areas. And Vince probably isn't joining us because I think it's 1,000 degrees below zero in Calgary this week. And I have heard from my coworkers in Austin it was about 80 Fahrenheit, so they definitely said hi. And you see, Len here is from Saskatoon, so it'll be cold there. And you could stand on a tin can in Saskatoon and see all the way from the Ontario border to the almost the end of the Alberta border. So anyway, it's great. It's Canada.
Yeah. Hey, Mark, how's
Yeah.
it where you are?
It has been raining the last few days, which, as a Californian who has lived through I don't even know how many droughts, I am very happy to see. We've gotten several inches of rain in the last few days, which is good as long as it doesn't happen so fast that it all just runs off before it sinks into the ground and collects into our reservoirs.
Oof.
It's been a little cold, but 40s or 50s, so cold by California standards, which the rest of the world will laugh at. We don't have real weather here, George. We just have to accept that. We are
No.
weather wimps.
Well, I'm just glad we get rain. Yeah, that's our version of
Yeah,
snow
yeah,
out here.
yeah, we
Well,
need it.
so this live stream came about because the other day, uh, Mark, you were doing your live stream, and someone asked the question. Ed, I think it was, said, "You guys should do something on the analog discovery," and I thought, well, that's a great idea. So here we are. So by popular demand of one person, we decided to do a stream about the analog discovery, which is this gadget here.
We're easily
So
influenced.
so yeah, it doesn't take
Yeah.
much, as you can
It does
tell.
not take much.
No, we're wanted to do something like that anyway,
Yeah.
and we thought this would be a good opportunity. So what we're going to do on the stream is give you an overview of what an analog discovery is, and pretty much everything we talk about is equally relevant to any kind of oscilloscope or signal generator. We're just going to illustrate it with the analog discovery, but unique to the analog discovery is that it has a really fantastic software user interface. Unlike a lot of these kind of gadgets that don't have very good software, this one is actually exceptionally good. So we'll talk a bit about
Waveforms.
the 82, how it works, and we're also going to take a little bit of a dive into some very simple analog circuitry design, because just showing the test equipment by itself without something to actually test isn't all that interesting. So we cooked up a little test circuit here, and so we'll explain how to do a simple audio amplifier with an operational amplifier or an op amp, and show you basically how the circuit works and how you could probe it. And we'll build a little low pass filter, which is pretty simple to do, and you'll kind of get an idea how the equipment works. So I think that covers most of what we're going to cover in the stream here. Do you guys want to add anything?
I've already given Mike and George permission to reel me in if I go too deep on what it is the amplifier circuit is that we're doing. If y'all want that, I hate guys. I hate YouTubers who say, "Hey guys," sexist. Anyway, if y'all want that deep dive, tell me, and we'll go over to my channel and we'll do the deep dive onto how op amps work. This live stream, the op amp is what we're using to demonstrate the AD2. The primary purpose of this particular stream is to talk about the AD2 and what it does and what it's capable of. And a lot of that, like Georgia was just saying, is transferable to other scopes and signal generators as well. But we like the AD2, folks. We like the AD2 as a product. We still have a coupon code, don't we, George?
Yeah, it's Ham Radio Workbench 2021. We're talking to the Digital Link guys to see if they're going to refresh it for 22. They haven't decided that they're going to do it yet. I think they will, but they'll probably need to come up with another code. I think we could probably imagine what the code would be.
I don't know,
man. We haven't closed on it yet, but hopefully we will after the first of the year.
So what I hear is you've got 5 more days to be sure you can go in and get that discount on your 82 bundle pack.
Yeah, actually, that's really true.
Yeah.
That's a fact. And after that, I don't know. Hopefully.
So 5 more days to guarantee you can get that $130 discount on the bundle pack. I mean, it's a screaming deal. Go get it. These things are fantastic.
Yeah, it's really cool. So we'll get into that, what it can do in a sec. Mike, you're going to be monitoring the YouTube stream chat. So if anybody has questions, put them in the YouTube chat. We're going to record this and people can watch it later if you didn't get to see it live. And we would also like to get any feedback on doing live streams. What kind of topics would you like to see, and do you find this useful? What would you find as useful as additional topics? Mike, do you want anything else before we kind of dive into this?
No, not yet. I think I typed in the coupon code Ham Radio Workbench 2021 in the chat. So
yeah,
great. All right,
carry on, guys.
All right, I'm going to go ahead and zoom in, and let me change this up a little bit. So I'm going to go ahead and leave the layout here. And Mark, if you think I should zoom in more, let me know, but we'll just go with this for the moment.
Sounds good.
Alrighty, so let me just give you kind of the quick tour of the analog discovery. So as you can see here, let me get my big mug out of the way here.
I was going to see how you were going to do this before I suggested that you did change that.
Yeah, you really don't need to look at my face for this. So let's focus on the stuff more than the face. Okay, so this is the analog discovery. It's only a few inches on the side, about 3/4 of an inch tall. So what you see on the back here is a micro USB jack, and that's how you get the thing power and data, obviously. There's also an auxiliary data input jack on the side here. I never use
power input.
I'm tested data.
You did.
Yeah, thank you. There's a power input jack there. There's also an audio output jack over here, which I also don't really ever use for my applications.
I never noticed that.
The thing that's kind of fun to note here, if you flip it over and look at the bottom, you can see through and see all the components in there. And I think the reason that this thing is called an analog discovery is that all of the integrated circuits that are used to make the device are supplied by analog devices. So analog devices is one of the largest manufacturers of analog mixed signal and RF integrated circuits. They make all kinds of analog to digital converters and precision instrumentation amplifiers and all kinds of other stuff. So they're really quite an amazing company. They have an amazing catalog of components. So this design was done all with ADI integrated circuits. So that's pretty awesome. The other thing, the business end of this, if you see here we go, the front end of it is a big header connector. It's a 15-pin by 2-pin array of headers, pins. And normally the way this is really designed to be used as a piece of test equipment is you get a couple of like oscilloscope leads, and you get this breakout board, and this board plugs into the front of this thing. So it makes a convenient way to connect, and it passes through all of the various signals. 99% of the time, I don't actually use the oscilloscope probes. You really want to use these if you're going to measure a signal that's at the upper limit of the frequency capability of the device. But for most of the stuff I do, which is usually analog or slow speed digital, I actually don't bother with the oscilloscope leads. So we're not even going to use those today.
So can I ask you a quick question?
Yeah.
What is the frequency range of the 82?
I think the top end spec is 10 megahertz.
Okay, and that's with the scopes, with the probes.
The scope probes. Yeah.
Yeah.
So
with the fly wires,
yeah, you can use the wires for anything that's like less than, I'd say, half a megahertz, somewhere around there.
Okay.
So if you're doing anything in the audio spectrum, which is well under 100 kilohertz, the individual wires are actually okay.
Yeah.
And I just slip them on there, so it just makes it convenient. I'm going to zoom in this picture here to show you what all those pins do. So this will give you an idea of what the physical layout is. Oh, that even came out. How about that? So you can see all those pins from left to right. So on the far left, the upper row and the lower row are scope channel 1. So in an oscilloscope, you have the main signal referenced to usually ground, but the ground side could be floating. In other words, not hooked to ground. So you have the 1 plus 1 minus pins. That's for scope channel 1. The next pair of pins over is scope channel 2. So it's a 2-channel oscilloscope, meaning you can put 2 individual signals separately into the device and look at them individually. The next 2 pins over are ground. In the 4th column, there's a built-in power supply. So the upper pin is positive voltage. The lower pin is negative voltage. It's pretty limited. You can set the voltage from 0 to, I think, 5 volts. So it in a fairly limited amount of current. So it's enough to power a few components for testing, but it's really not like going to replace your bench power supply. So I don't use the power supply very much. The next pins over, column 5, is waveform generator 1 and waveform generator 2. So just like you have 2 oscilloscope inputs, there are 2 independent signal outputs. So those signals could be anywhere from 0 to a few megahertz, and you can set the wave shape, whether sine wave, square wave, whatever. We'll get into all that. So you have 2 separate signal generators, more ground pins. There's 2 trigger pins, T1, T2. Those are used for external triggers for the oscilloscope, which you don't typically use because the built-in triggering is fine in most cases. And then the rest of the pins, the upper 8 pins and the lower 8 pins to the right, are for digital I/O signals. And you can set them for either inputs or outputs. So you can flip a little icon on the screen to change the output state, or you can use them to measure, like a logic analyzer, the digital values coming in. So you can measure the 1s and 0s on a bus or whatever pins you want to look at. So what you really have with the 82 is a multi-function piece of test equipment. I got mine mainly as an oscilloscope, but I use the signal generator probably as much as I use the scope. And I occasionally will use the digital I/O, but mostly I use it for the scope and the SIGGEN.
Can we take a brief, very brief kind of explanation of what an oscilloscope is and what a logic analyzer is, and just in case anybody doesn't know what those are or what they're used for?
Yeah, that's a great point. Let me change this.
You want me to?
Yeah, go ahead.
Okay, so a oscilloscope. In case you don't know, an oscilloscope is a device that lets you look at voltage over time. So if you put the scope probe onto a pin or whatever that has a signal, like a varying voltage signal on it, it will actually draw the voltage over time on the screen. And that's a analog voltage, right? It can be somewhere between 0 volts and 5 volts in this particular case, because that's what the analog discovery has as a range. Actually, I think it has built-in voltage dividers, so it can do higher volts than that. But it's a range. It's an analog signal, anywhere between the minimum and the maximum voltage. A logic analyzer does the same thing, but it's binary. So it looks at a signal. You can tap a signal on a circuit, and it measures whether it is a 1 or a 0 over time. And so you can, let's say, like you put it on a serial bus, like a UART serial bus, and you can actually see the 1s and 0s going down the wire on the logic analyzer. And so you've got 16 channels that you can use as digital inputs as a logic analyzer, or you can use some of them as outputs if you want to use them to control something on the device that you're testing. But that's the main difference between an oscilloscope and a logic analyzer. They're both doing the same thing of measuring a signal over time, but the oscilloscope does it with a analog voltage and with some amount of precision, and a logic analyzer does it with binary, either a 1 or a 0. It's either high or a low.
Right,
So
and
like
a voltmeter would only show us instantaneously at this time, and
At
sometimes
this time,
we need to
exactly.
see some history, some
Yeah.
pretty quick history sometimes, but history.
Yep.
Okay.
So in the little
Perfect.
diagram here, if you think about like Mark, you were saying, an analog signal over time, that voltage is going to vary. And what the oscilloscope does is it samples periodically at various points, and then it'll draw. Well, it'll sample real time, and it'll draw on the screen what the shape is, and this corresponds to the voltage in this case here. So voltage is expressed on the vertical column. So here maybe it's 0 volts, and then you start to go negative, and the resolution is pretty fine. I mean, it's down to, several points of precision. So you'll get, minus.
Is it 10-bit?
I'm not. It's better than 10-bit. I think it's 14.
I got it open here, so I'll let you know in a minute.
Yeah, I think it's 14, but Mike, you can check it out. So what the number of bits tells you what the resolution is in the vertical axis. So if you had an 8-bit resolution, that means 2 to the 8th is 256. So you get 256 shades of gray in the resolution of the voltage. If you have 10-bit, you have 2 to the 10th or 1024. So 1,000 different levels of resolution or grayscale, if you will, of voltage. And if you go to 14-bit, then it's whatever, 32,000, I forget, whatever.
16,000.
16,000 samples.
A whole lot.
So every time you add more bit of resolution, you get a lot more detail. So you can really finally measure it.
14-bit.
14-bit, so 16,000. Yeah.
Yep. So for a piece of, so this is really a good point, by the way, if you're looking at a digital oscilloscope, you really want 14 bits of resolution or better. You may see 14 or 16 or even 24, but 14 is good. Anything better is better. Anything less than 14 is a coarse measurement. A lot of microcontrollers have 10-bit analog to digital converters, which is good enough to measure like a voltage in a power supply, but it's not an instrument level resolution. So that's something to look for. And the thing that determines it inside the instrument, the core chip, is called the analog to digital converter, and that's the device which has that resolution. And
you can think of a logic analyzer as basically a 1-bit oscilloscope.
Yeah, it's the worst resolution of all. So like if you have a square wave like this and you're sampling, what's going to happen is it's going to look at this and go, okay, well, anything below a certain threshold, that's a 0. Anything above that certain threshold, that's a 1. So you're only going to get, like Mark said, a 1 or a 0, as opposed to this where you get, minus 0.2358786 volts. It's much more granular in its measurement.
Cool. Okay. Thank you for taking that brief detour.
Yeah, it's great. So let's get into the 82 a little bit. The simplest thing to do that we're going to start out with, if we have our analog Discovery 2 or whatever your oscilloscope is, we're going to have one port on it, which is our signal generator. And then we're going to have another port on it, which is our scope input. And the simplest thing that you could really do to illustrate any of this stuff working is take the signal coming out of the signal generator and shove it back into the scope, and basically just put a wire between the SIGGEN and the scope. And so we'll start out with that as an example. So what I'm going to do physically here, you can see with the 82, I'm just going to run the signal out and back in. So I put in one wire. The green wire here is the oscilloscope input, and the yellow wire is the signal generator output. So I've got a little shunt that's just a 2-pin header that's soldered together. So when I connect these two guys together, basically it's just doing this. It's taking the signal out of the SIG generator and looping it back into the scope. So what I'm going to do now is bring up a screen and launch the software.
Can you maximize yourself and put Mike and I off to the side again?
Oh, you bet. Thanks.
There we go. Thank you.
Okay, so let me make this software bigger. So when you launch the Analog Discovery software, the software is called Waveforms. Clever name. Wonder why it's called that. So when you launch the software, it comes up and it says, hey, I've found, in this case, 2 USB connected instruments. And so I have 2 of them here. I've got the first one, this ADP 3450. That's a 4-channel version of this thing that I'm showing you here. And then this next one down is the Discovery 2. And that's the one that we've got on the bench that I'll be demonstrating. If you want to download this software and play around with it, there's a demo mode. So you can see here, there's a demo. If I don't have an instrument but want to play with the software, I could select demo and manipulate the software as if I had an instrument hooked up to it. So it's a fun thing to play with. It's free, so you can download
And
it.
it works in Linux. I am very happy to report.
Yeah, it works on Mac and Linux and Windows. So I'm going to select the Analog Discovery 2. Oop, if I click on the right screen, I'm going to select it, and then it's going to connect to it. And so now I get the top palette of instruments. So when we talk about the 82 being basically a SIGGEN and a scope, you can see on the left-hand side here, those are only the first two features. So scope and WaveGen are the two that we're going to play around with. In addition to that, there's the power supply, there's a digital voltmeter, there's a way to log data, so you can actually hook this thing up to a device and store the data periodically and dump it to a file. There's a logic analyzer, pattern generator, static I/O, which is like switches and LEDs. It's pretty fun. There's a spectrum analyzer. This is not an RF spectrum analyzer. That would be too good. That would be awesome. But this is an audio or low frequency spectrum analyzer. And I've used it to do things like filters. So it's useful. You can see what the delay is at different frequencies and that sort of thing. Network analyzer, impedance bridge. There's a protocol analyzer for some of the common digital bus protocols like SPI and I2C. And there's even a scripting language. So if you want to do a repetitive test, like I want to generate a signal, take a measurement, change this input signal, take another measurement, do that 1,000 times, you can write a script to control the instrument, so you don't have to do it manually. So it's pretty powerful.
Very good for testing automation.
Yeah, it's awesome for like if you build a project and you want to beat it to death, you can hook this up as a signal source, either digital inputs or analog signal inputs, and take measurements and store all that, and then come back in a couple hours and see if it worked or not. So it's
or if you're going to make 100 of a thing and you want to test them all.
Yeah. So I'm going to first of all pick the scope. So I just click on scope.
I think you're on OBS again. We can't see your cursor.
I'm clicking on OBS. Too many screens. All right, so I'm going to click scope, and so the first window that pops up is my oscilloscope window, and you'll notice in the upper right-hand corner there's a big run button. When
can you move your head down to the bottom corner, because you're covering some important stuff?
Am I really? Let's see.
Yeah, your channel information is being covered right now.
Ah, good point. Let me figure out how to make that happen.
Go over to OBS and just drag your face down.
Yeah. I need OBS to let me grab the handles. There we go. Hang on. There we go. Technology.
Perfect.
All right. Is that more better?
Yes, much. Thank you.
I could make me go away completely. That'd be even better. All right.
I don't know. So, Marty would be upset.
When you first start the instrument, it's in the pause mode. Any modern oscilloscope has a run stop button, which is funny because in the old days you'd get an analog scope and you turn it on, it just ran. There was no notion of stop. So you have to hit the run button to get it to start. Okay, so I'm hitting OBS again. I got to stop doing that. Okay, hit the run button. So now it's running, and I'm just going to leave the yellow channel turned on. And you see no signal. So it's a flat line. That's because it's looking at the signal generator, and the signal generator is not generating a signal. So now we're going to bring up the signal generator. I go back to my top palette of instruments. And so I pick WaveGen. That's the second box down. And so there's my my signal generator. And I do want to get both of these on the screen at the same time. Now, one of the things I love about this thing is that on a normal oscilloscope, you have the screen with the waveforms on it, and that's it. And you'd have a separate box that's a signal generator. It may or may not have a waveform on it. With this software, you can have as many screens as you want, as many windows, and you can arrange them in any configuration you want, and you can save that configuration off. So you can have like 2 signal generators, an oscilloscope, and a digital pattern input thing, and just save that as a template, and then launch it the next time, and all the stuff comes back up the way you left it. So that's super handy. So now if you look at the signal generator down at the bottom, it comes up with some parameters. So I'm going to want to point your attention to the left-hand side of the screen, where it says sine. So the signal waveform type is sine wave. The frequency is 1 kilohertz. The amplitude is 1 volt, and there's no DC offset. There's no vertical offset. So I'm going to hit the run button, and as soon as I hit the run button, guess what happens? You notice the oscilloscope pops to life, and now I see a sine wave on the oscilloscope. That's because I'm taking the signal out of the SIGGEN and looping it into the scope. And if I change any of the signal generator parameters, you'll see that on the scope. So let's say if I go back to the signal generator and I change the waveform, I can have a DC signal, which is just a voltage that's flat over time, not very interesting. Sine wave, very popular. I can pick a square wave, useful. Triangle wave, could be useful. I could do a ramp up, a ramp down. I could generate noise. I could do an individual pulse, trapezium, etc. You can also give it your own custom weird waveform shape. If you have some odd shape that has different voltages at different increments over time, you can give it that. In a simulator, if you're familiar with a SPICE simulator, that's called a piecewise linear input form. So each individual segment is a small linear variation, and they could all be quite complicated. So you could give a PWL kind of equivalent input. That's often in instrumentation terms called an arbitrary waveform generator. Arbitrary because it's not a uniform standard thing like a sine wave. It's low for this long, then it ramps up to this voltage, then a little bit later this voltage, and off you go. So that's called an ARB in the biz, arbitrary waveform generator. We're going to stick with something simple. Actually, I'll go ahead and pick one of these. Like, what's your favorite waveform, Mark? Pick one.
Let's go with square.
Okay, square wave. So I'll just click square, and then you see both the output signal on the bottom window and then the waveform on the scope snaps to it immediately.
I could great educational tool. It really is, isn't it?
Yeah. So if I want to change, let's say the frequency, by the way, it's kind of hard to see on the stream, but the next little window down says frequency. It says 1 kilohertz. I can pull down that and I can change it to these popular, commonly used frequencies. Like, let me go from 1 kilohertz to 10 kilohertz. Guess what? There's a lot more lines on the screen because it's now 10 kilohertz at the same sample rate.
Yeah.
I can also just leave my cursor on top of that little window that says 10 kilohertz, and I can roll my mouse button, and I can actually scroll through and manually sweep through a bunch of different frequencies, which is kind of useful at times. So the user interface is super intuitive, and this was a big pleasant surprise when I started playing with this, because a lot of the software for these kinds of things are functional but cumbersome.
Yeah.
And the guys that wrote this software, I think, did an outstanding job. The UI, the user interface, does not get in your way. It's pretty powerful. We could do something kind of even more interesting that's really useful. Like if we go back to sine wave, right above there, it says simple. Simple just means this waveform repeatedly. I could click on simple, and I can pick a custom waveform. I could play a file, like I can have an audio file I could play, or just a table of numbers, or I could do a sweep. Sweep's pretty useful. So if I pick sweep, now you notice the screen changes, and it gives me some new fields I can fill out. So there's a sweep to, because our base frequency is 1 kilohertz. Now it says sweep to 10 kilohertz. And how long do you want it to take to sweep to there? So it's right now 1 millisecond. So I'm going to slow it down a lot. I'm going to make it 5 seconds.
So this is going.
Yeah. Actually, I should have hooked this up to a speaker, because it'd do exactly what you did, Mike. It'll go.
Well, I figured you were going to do that later.
Yeah, that's a great suggestion.
This would have been. This is great if you're sweeping a audio filter circuit.
Yep.
Yeah.
And you want to see where it attenuates more. And
right. And now, by the way, a lot of times you'll hear someone in audio say, "Oh, that audio circuit is flat." What they mean by that is a signal at one frequency that you put in at a certain amplitude, you'll get that same amplitude out, or whatever the amplifier is supposed to do. Let's say it's a unity gain amplifier, 1-to-1. You put a volt in at a kilohertz, you get a volt out at a kilohertz. That's a unity gain amp. if you put a volt in at 10 kilohertz and you get 1 volt out, that's flat. In other words, it doesn't change the amplitude with the frequency. If you're, and sometimes you want that. Like if you're making a mixer, you really want that. You want everything that comes in, low or high frequency, to come out the same way. But if you're making a filter, like let's say you're making an audio low pass filter because you want to eliminate high frequency noise, then you want low frequencies to come out at the desired level, but you want very high frequencies to get attenuated. And so if and we'll do a low pass filter here in a little bit. With a low pass filter, you'll see it roll off. And of course, you can change the frequency range or the wave shape or the speed at which it does this. But this is a
George,
super useful thing.
Can you stop the sweep for a second? I want to check something out. Your video just went to horrible quality as soon as you started the sweep, and I think just the
refresh rate is too slow.
It's not the refresh rate. It's the bit rate. It's the MPEG bit rate or the 264 bit rate, because the screen is changing so much.
Oh, there it goes. You're right.
It's having to dedicate so much of the of
frame grabbing.
Yeah.
Too many bits to change.
Yeah.
Okay, so that's sort of the basic idea of the signal generator, and then the scope. Over on the right-hand side of the scope, there's a few things here. There's 2 channels. You see the blue line and the yellow line. If I wanted to move the signal over to the blue one, I could just move it to a different pin, and then the blue line would look like a sine wave. And then for each of these inputs, you can set what the voltage is, and also what the offset is. So like here, I can change the vertical sweep. So let me go ahead and turn off the SigGen. So we'll just look at the scope. Oh, we don't have a signal generator, so I'm not going to see a signal. That was dumb. Let's go back here, turn on the scope for the SigGen.
You already have the tab open.
Oh, there we are. Oh, scope, WaveGen.
Hit run all, yeah. Or
no, it's just not there. I probably have the window hidden somewhere, and I don't see it. We're going to do this the quick and dirty way. If all else fails, pull the plug.
Have you tried turning it off and on again?
Have you ever worked technical support? All right.
I grabbed a real scope, so when we're ready, I'll show you what this replaces.
Actually, we can do that in just a sec here. That'd be good. Okay, so there we go. So there's the blue line is channel 2, the yellow line is channel 1. We can change the vertical range. And I know you can't see this probably on the stream, but this is a 1 volt peak-to-peak signal. And so like right now, my range is +5 and -5 volts, which is why it looks so small. And I'm just rolling up and down with my mouse.
I'm going to keep you honest here too. I'm going to keep you honest because there are different volts if you're new to this, and the difference between peak to peak and RMS.
Oh yeah.
And your VOM, you all own regular voltmeters, right? They measure RMS, and scopes will show you peak to peak, but you may have a meter in there that will show you both in a number.
Right.
Does it?
I bet it does. I have no idea where it is. It probably isn't there somewhere.
There's a little formula to figure out one from the other. So
well, yeah, RMS is about 2/3 of the value of the peak-to-peak voltage. I mean, very round numbers.
0.7, yeah, 707.
Alrighty, so that's like the super basics. So to make it a little bit more interesting, we're going to actually put this through a real electrical circuit. Are there any questions in the chat, Mike?
I'll just warn you that Rod's now watching.
Uh-oh, we better watch what we're saying.
That's right.
No, we're good. The only question to chat was my inability to see the screen go worse, but I had it on such a small one.
Okay,
we're going good.
All right, so we're going to take a quick diversion into analog circuit design, because what I want to do is show you this little test board, and it's just a black box unless we really explain kind of what's going on with the circuit.
And I promise to keep my mouth shut.
Good luck with that.
Yeah, I know.
Okay, so what does this thing do? So to show you like a typical analog circuit, we thought we'd use an operational amplifier, op amp, because you find them a lot in zillions of different circuits. You can use them for little audio buffer amplifiers. You could use them for mixers. This is just audio applications. You can make filters out of them. You could do all kinds of things with them. So this little component here is a little 8-pin package. Inside this package, there are actually 2 op amps. You can get this with 1 or 2, and there's a double size with 4. And the symbol for an op amp looks like this. So like Mark said before, we can go into a whole dedicated hour session on what does an op amp really do. So we're not going to do that today. What we're going to do is just talk about how an op amp will work like a black box functionally in order to show an example of an oscilloscope sweep circuit of a low-pass filter. So to do that, we'll just draw a typical kind of reference design with an op amp. Typically what you do is you have a input resistor going into one input, and then you have a feedback resistor across the input and the output. The simple way to think about the way the op amp works is if you have a signal coming in, let's say we want to have a signal here coming out, the amplifier, being an amplifier, will have a certain amount of gain. So for a given level input, it'll give you some amount of output. And in an op amp circuit, that gain is determined by the ratio of these 2 resistor values. So if I have a 10K resistor here and a 10K resistor here, that's 1 to 1. So if I put 1 volt in here, I'll see 1 volt coming out over here. So it's essentially a buffer. It's an amplifier of no gain, 0 gain. Now, why would you want that? I mean, you might just want a buffer, or you might be building this into a filter. So you don't want to change the level. You just want to change the frequency response. Or maybe you do want to amplify it. If instead of 10K, let's say I made this 100K resistor on the feedback, I now have a ratio of 1 to 10. That's a gain of 10. So if I put 1 volt in here, assuming this op amp could go to this high a voltage, which many cannot, you'd see 10 volts coming out here. A more realistic example is if I had 100 millivolts, 1/10 of a volt, 100 millivolts coming in, I'd have 1 volt coming out. So it takes that tiny little signal and amplifies it. So right away you can think, well, that may not be enough to drive a speaker, this op amp, but it might be enough to take a low-level signal coming off of a receiver and boost it up enough to actually run it into a speaker amplifier. So that's a simple example. This is a configuration that's called an inverting amplifier. Inverting means that whatever goes in here is inverted on the output. To your ear, it will make no difference at all. So it's almost not worth bothering with, but I just thought I'd mention, because someone's going to say, oh, it's an inverting amplifier. The other thing is, most of the time, this positive input on the op amp is referenced to ground. There's a positive voltage and a negative voltage to power the op amp. In the classic op amp circuit, being an AC signal is referenced to ground. In other words, the sine wave goes from 0 volts to the positive rail, or whatever the maximum voltage is, and then down to minus that many volts, and then back up again. So you need let's say a positive 10 volts and a minus 10 volts, or a positive 5 volts and a minus 5 volts, and then you hook this pin to ground. That's classic op amp circuit design. Now, the problem with that, there's a couple of problems with it. One problem with that is that now you have to have a plus and minus voltage power supply. If I run my circuit off of, let's say, 12 volts DC, then I have to create minus 10 volts. Making plus 10 volts is no big deal. Making minus 10 volts is another power supply circuit, which is a pain. So there's a trick that a lot of us use in designing audio circuits, which is to raise the reference voltage here from 0 up to halfway between this and this voltage here. So a lot of times what we'll do is we'll make this negative supply ground, and our positive supply will be whatever our voltage is. In this case, we're going to use 5 volts as our power supply rating. So ground and plus 5 volts. So then the question is, well, what should this voltage here be? So there's a quiz question. What do you think this is? Should this be ground or something else?
Ooh, pick me, pick me,
Okay, Mark,
pick me.
what's the answer?
You want it to be about halfway between your voltage supply and the ground.
Exactly. And so our voltage supply is 5 volts. So ideally, we want this to be 2.5 volts.
And that's
And we'll
assuming your sine wave is symmetric, which it is.
Yeah, in the simple case. And
Yeah.
so 2.5 volts here, we'll put a little resistor here, a little current limiting resistor going into it. We'll make that guy 10K also. So now I have a basic amplifier that'll work off of, a 6 volt or 9 volt or 12 volt battery with a regulator to bring this down to 5 volts. Everything is referenced to ground. So that'll be fine and dandy. Except for the fact that my analog audio that's going into this may still be going up and down relative to ground. And so to make that work, we're going to stick a capacitor in front of it. And we might as well stick a capacitor out here. Why do we do that? If we stick a capacitor in series, a capacitor is a DC blocking device. DC doesn't go through it. So what happens is, regardless of what the AC signal is referenced to coming in, it's going to pass that AC component over here. And so it lets us raise our voltage reference up to that 2.5 volts with no problem. So that's kind of a handy trick. So that's the circuit that we're going to show here. If we actually look inside one of these parts, one of these pins is ground, and one of these pins is hooked up to positive 5 volts. I've got 6 pins left over, and I mentioned there's two op amps in each of these packages. So this guy here is going to be hooked up like this. And there's another one over here hooked up like that. So the way these chips work, whenever you see these kind of symbols, these are completely isolated, except for the fact they share ground and 5 volts. The electrical circuitry between these two op amps, even though they're in the same package, are electrically isolated, so that any signal going in and out of this op amp will have no bearing on what's happening over here. They might as well be two different parts. So in the sample circuit here, we're using this op amp on the right-hand side over here. So you can see there's a couple of resistors. So that resistor there is the bias resistor. This resistor here is the input resistor. Oh, look, we're missing a resistor. Where's the feedback resistor? So the feedback, you might notice this says feedback. So big tip. So I just routed the pins, the wiring that goes to those 2 pins to these 2 blocks here. So all of these 6 sockets are hooked up to one side of this, and the other socket is hooked up to the other side. So I could just plug in the feedback resistor. So for illustration purposes, I can unplug this resistor and plug in a different resistor, and we'll do that, and you'll see the gain change.
The advantage of the 2 op amps are one case too, in case you just happen to blow one up. You got a spare?
Well, actually, we're about to use the other op amp. Because in my circuit, I've got a 5 volt regulator. Okay, so I've got maybe a 6 volt battery and a 5 volt regulator, or a 12 volt battery and a 5 volt regulator. So that's simple. How do I create this 2.5 volts? Because I need to come up with 2.5 volts to give this thing the right bias. So I'll just give you a quick answer. I'm going to use this other op amp as a voltage divider buffer. So if I take, let's say, 2 resistors and put them in series between 5 volts and ground, and I'm going to make this 10K and I'm going to make this 10K. At this point here, I have a voltage divider. And so at this point, what voltage am I going to see here in the middle?
2.5 volts? Halfway?
2.5 volts. Halfway, because it's 10 and 10. If these are like different values of resistors, that ratio the voltage will be dependent on the ratio of the values of the resistors. But if they're both 10 volts, that voltage is half of the supply voltage. So this is 2.5 volts now. Now, the good thing is I could say, well, I'm going to just take this 2.5 volts and hook it up to this input here, and I'm done, right? Kinda. What's a little bit better practice is to actually use this op amp as a buffer. That way you can supply a little bit more current and you'll have a nice stable voltage reference. So
And
you
this-
could actually hook this up and it would work fine, but it's kind of best practice to hook this up to another
So George,
op amp. Yeah.
So in the basics here, and not to get too far in the weeds, why didn't you use two 5Ks or two 20Ks or two 200Ks?
You could absolutely could.
Because 10Ks are cheap.
Right. Because
And you had
when
1,000.
when you needed 5 10Ks and you ordered a DigiKey, you ordered like 1,000 of them because they were cheaper that way.
Okay.
So that's also like back up here, the ratio is what's important. I could use 1K and 10K, 10K and 100K, 100K and a meg. It's a
exactly
1 to 10
the same
ratio.
thing.
It doesn't really matter. It's just the ratio. But Mark's exactly right. It's because they're readily available. So I'm going to take this guy. By the way, there's my inverting and non-inverting inputs. I'm going to hook this to my non-inverting input, and I'm going to take my inverting input and hook it up to my output. And this is now my bias output, my 2.5 volt buffered output. So I've used 2/2 of my op amp chip to create a really stable 2.5 volt reference to bias this guy. So now I can raise this up and operate this guy with a 5 volt rail. So this has nothing to do with how to use an oscilloscope. But if you're designing analog circuitry, this is like useful tip number 1.
Yep.
And that works at DC levels.
What's that?
And that works at a DC level because we think as
Yeah. And if you had, let's say, a big mixer, like let's say you have 5 of these op amps, this one op amp with this nice solid 2.5 volt output could be used to bias all of the op amps. So you don't need to do this for every single one. You could do this once and then use this to actually supply that bias voltage. You're hardly pulling any current at all. It's just meant to be a stable voltage reference.
Yeah. Come talk to me if you want more details on this. I think we're going too far into the weeds for this particular live stream, but if you are curious about this and want to deep dive on this some more, let me know and I'll do a stream on my channel for it.
Alrighty, so now let's get back to the scope. So I just really wanted you to look at this and not think like, what in the world is on here? So let me just redraw our basic circuit here. We've got our input, our feedback, a decoupling, or not, a blocking cap. So here's my input and here's my output. That's what's on this board. So what I'm going to do now is I'm going to hook it up to power. So I'm going to take my 5 volt power supply, hook that up.
No magic smoke. Okay, that's a good start.
Thank goodness.
Yep.
I've got both little wire loops and headers here. So I'm going to hook this guy up to ground. So my analog discovery has a ground reference. I'm going to take my my shunt off. So now you can see the scope goes back to nothing. I'm going to put my signal generator on the input pin, and I'm going to put my scope on the output pin. And then I'm going to shut off my channel 2 on the scope because we don't need channel 2. Okay, so there we are. So now the signal is going through the op amp here. So the sig gen goes in here through the cap into the op amp, 1-to-1. So I get the exact same output coming out the other side over here. And just to show you it's really working, if I pull off the signal generator wire, then the scope will go to 0. Okay, and I can go back and let's say sweep my input from 1 kilohertz. Let's roll up to, here's 20 kilohertz. Here's 200 kilohertz. Did you notice something starting to happen? Here we are at 2 megahertz. Here's a megahertz. What does that tell you? What do you see that's happening on the screen?
we're losing gain.
That's right. We're losing the signal. At some point, that output signal is dropping like a rock. And when we get up to here, that signal's completely gone. And it's hard to read on the screen here, but that's at 10 megahertz. So I've got a 10 megahertz sine wave that now is completely attenuated. I bet if you look at the spec for this part, it's only good to probably a megahertz. So no wonder it falls off a cliff.
So are you saying I can't get on 30 meters with this?
I'm saying you can't get on 30 meters with this. Now, if I go back down, here's 500 kilohertz. The signal's there, but it's pretty small. At 100 kilohertz, we're kind of back to normal. So you can see as I sweep it up here, you can see how the signal goes down. Now let me go back to my sweep function, and I'm going to say I want to sweep from let's say 10 kilohertz.
It's still pretty amazing, isn't it, for a device?
To 200 kilohertz.
Just slow it down, please.
Hang on a second while I slow this down.
And stream, don't be surprised if the resolution goes to crap when he's got that much updating on the screen. Excuse me, it just kind of starts running out of bits in the H.264 stream.
You know, I'm watching while you're doing this, George. People are actually ordering the bundle. So the guys are actually going to come into work tomorrow and go, WTF?
So what you're seeing here is I've set this up so the signal generator starts at 10 kilohertz and then goes up to 200 kilohertz. And it does the entire sweep in 5 seconds. So those are 3 parameters I could just set on the screen. And you can see the wave, you know, it's long and it squishes in as the frequency goes up, right? The wavelength is going down and down and down. Now, if you really look closely, you can see that the amplitude goes down a little bit, but not a whole lot. So I'm going to zoom in just a little bit on the oscilloscope. Okay, so now I'm looking at 200 millivolts per division on the display. So essentially plus and minus 1 volt. So you can see at the very end at the highest frequency how the waveform is just a hair below the edge. Let me make this a little bit bigger. Oop, let's not do that.
Do it in OBS, not in... There you go.
So you can probably see it a little bit better. So the sine wave is right at the edge until the very end of at the highest frequency, then it starts to drop a tad. Okay, so far so good?
Roger.
Yeah.
Okay, so now we're going to do something interesting, and we're going to make a low-pass filter. So a simple way to make a low-pass filter is to come back to our schematic here. If I put a capacitor in parallel with that feedback resistor, that is going to cause the op-amp to behave like a filter. And so I happen to have a 0.1 microfarad, little capacitor. So I'm going to...
You still have a 10K on the feedback?
Yeah, there's still 10K on the feedback. So I'm going to stuff that capacitor in the little block here and put it in parallel with the 10K feedback resistor.
Oh, wow. Really? A 0.1?
Yeah.
Okay.
Mark said he'd be quiet.
I'm biting my tongue.
So that pretty much killed our high end, didn't it?
It killed more than that.
Yeah, your cutoff is at 160 hertz. You'll want That's why I was asking why you used a 0.1 because
let me grab a smaller one.
Yeah, you'll want one like a 1 nanofarad or a...
So we could make our own CW filter here.
Yes.
Essentially.
Yeah. George, the other alternative is to use a smaller resistor.
Yeah. Or change the frequency range. Only just stick a smaller capacitor in there. That's just what I had sitting on the bench.
Yep. So the math here, if you are curious, is 1 over 2 times pi times r times c. 1 over 2 pi rc. And so R is the value of the resistor and C is the value of the capacitor. So 10K times a 0.1 micro times 2 times pi, and then take the inverse of that. And I've got a calculator on my phone that has that function built into it, and so it's about 160 hertz.
Let's put a 470 puff in there. That should make a
Yeah,
drastic
that'll do it.
difference. Okay,
So George,
here's-
while you're doing this,
Yeah.
is there a different view where we could sort of see what the RF guys would want to be looking for in a tracking generator, where we see it fall off?
what do you mean, Mike?
Do you know where in a tracking
Spectrum analyzer.
generator, like if you grabbed your IFR and you were doing your cavities at the RF level,
Mhm.
could I get a graph that shows where it peaks and then rolls off
Oh.
rather than
Yeah.
or an F? I was like,
Yeah,
anyway.
we could try that with a network analyzer. So if you,
but we can't do it with this.
well, you can do. We could give it a try.
Okay, carry on.
So here we've got this little dip monolithic
This works.
capacitor in parallel. So that's this cap here. So right now, this is 10K resistor, this is 10K, and this is 470 picofarads. And if you look at the scope now, you can see how when it's at its lowest frequency, we've got about a volt, a positive and a volt minus, so 2 volts peak to peak. And at the very end, as it gets to 200 kilohertz, look how it goes down and down and down. So at 200 kilohertz in frequency, it's down to about 0.4 volts. So it went from 2 volts peak to 0.4 volts peak to peak, just by sticking that capacitor in there. Now, as a filter goes, that's a very gradual slope. And if you wanted a filter that has a much sharper roll-off, then you'd have multiple stages, multiple poles, essentially, multiple stages, and you get a much sharper roll-off, which is probably what you'd do if you're really building a real, like CW filter. You wouldn't just use one capacitor. You'd use multiple stages to give you more of a sharper curve. But it illustrates the point, and the kind of thing that you could do with a scope and a signal generator. And again, if you look at the bottom, that the signal that's being generated is rock solid. It's a volt all the way across. And the only reason why you see any of this roll-off function is purely because of this capacitor.
So one other
One of
reason
you want to answer? Go ahead, Mark.
I was going to say, yes, okay, Stephen has got this exactly correct. So he says, so as the frequency increases, the impedance of the capacitor goes down, allowing the higher frequency content to bypass the op amp, the way I understand it, bypass the feedback resistor. So remember when he was talking about at the early part of this, that if you wanted to increase the gain of this amplifier, you would put a larger resistor on that feedback point, and that will increase the gain. It also stands to reason that if you decrease that feedback resistance or impedance, you will decrease the gain. So by putting a cap around that resistor, any frequency above the 1/2 pi RC point will have a lower impedance path through the capacitor and will therefore have a lower impedance on the feedback and will have decreased gain. Whereas frequencies above the 1/2 pi RC point, the dominant impedance there will be the 10K resistor, because the impedance of the capacitor continues to go up and up. But the lower impedance of the resistor kind of takes over at that point. So yeah, you got that exactly correct. One of the reasons, what I was going to originally say, one of the reasons you would do this is if you're only interested in having a audio amplifier, like I want to pass 20 hertz to 20 kilohertz, and I'm not trying to do anything at RF, you would put this capacitor around your feedback resistor to attenuate any RF that might get into this amplifier and decrease the gain to keep the amplifier from oscillating at a RF frequency. Ask me how I know.
Did you make
Been there, done that?
Did you make an oscillator out of an amplifier?
Yes, it is much easier than it sounds.
Yeah.
So
by the
you
way,
built your own whisper station, you're saying?
Exactly. Yeah. Except that it wasn't whispering; it was screaming.
So I just changed the to a different instrument. So this is the spectrum analyzer, audio. Well, not audio, but it's audio plus. So you can see the spike moving. So as the sweep generator moves across that frequency range from close to 0 to 200 kilohertz, you can see the signal move.
And it's harmonics. I love that.
Yeah, and it's harmonics. Yeah, chase the harmonic. Okay,
That's right.
so there you go, Mike. There's
What a
your
great example.
spectrum analyzer view. Oh, and just for yucks, we can just stop. I hit the stop button on the signal generator, or I could, let's say, go back to a simple view without the sweep, and there's just my static signal, right, at the 100 kilohertz, or I can move it manually with my mouse. So I could put
to a square wave.
Ooh,
Oh, that'd be interesting.
look at the harmonics.
Look at those harmonics. So yes, Steve, you're correct.
So actually, that's a really excellent idea here. So let's go back. Let's do this again. This is really worth pausing on. Okay, so this is a sine wave. It's a 20 kilohertz sine wave, and you can see the second harmonic, or probably the third harmonic here, and then beyond that, you can't see too much of the harmonics. But when we switch to the square wave, wow! So this does come up a lot. Like we talk about switching power supplies or other devices which are digital causing interference, and this is kind of a way to actually see that
exactly what they're
harmonic
doing.
component, the harmonic energy, is very, very high, and that has to be filtered out. I mean, that's why really good switching supplies have to have great filtering.
And
Steve,
why? Oh, sorry.
Go ahead, Mike.
Square waves are a collection of the odds harmonics.
Odds or evens, I can't remember which. Yeah.
Oh, that was a long time ago.
Yeah. Stephen Benke also points out that this is why you want a slower rise on your CW waveform. That's not so much a square wave as it is an impulse, but it's basically a square wave is a repeating train of impulses. So it's basically the same thing going on here. So what is this? Is this measuring amplitude?
So I wanted to put on the network analyzer view here. Run that.
I'm amazed at how fast it is, actually.
Yeah, it is pretty peppy. So now this is a way to look at this as another sort of spectral view. So remember, this is the sweep. We're going from one, in this case now, 1 kilohertz to 200 kilohertz. That's like the same frequency range. So remember when the sine wave, as it was going up in frequency, you saw the amplitude go down. If you look at the yellow line in the top window, that is the amplitude over frequency. So
what's the blue line?
That's the phase.
No, the bottom blue line is the phase. What's the blue line on the top graph?
The blue line on the second one. The first one you're talking about.
Yeah.
Good question.
Okay.
Let me see.
Feel free to proceed if I've sidetracked us.
Other channel.
Got it.
The channel 2. Yeah, because I was looking at the phase, and that's a blue line. Yeah, so we don't want channel 2.
Okay, so that's just the amplitude of the second channel of the scope that we're not using.
Right.
Which explains why it was down at minus a whole lot of dBs, because it didn't have any signal coming in.
Because there's no signal. Yeah, exactly.
Yeah. Okay.
Guys, using an oscilloscope or a piece of test equipment is the tool that will make sure you read all the graphics on the screen. Because sometimes you go, what am I looking at? And this is a great example. So, sometimes you just have to slow down. Plus, the ADD in me goes, okay, this doesn't look like I'm expecting, So there's always the information on the screen.
So if we want to measure it, we can actually look at the yellow line there. So at the very beginning, at a kilohertz, it's 0 dB down, right? There's no attenuation. By the time we get to 200 kilohertz, it's about 25 dB down, which is not bad. I mean, just for a cap. The thing that I think is so useful with this kind of an instrument is like I said, the user interface is very simple, simpler than, in my opinion, than most boxed instruments. And most other software. So it's fairly, even though it's a complicated topic, it's a fairly simple UI. The thing that I love about this is that you could play around with this, and a lot of us learn stuff visually better than we do mathematically, you know? So when you're doing things like a filter, looking at an equation for a filter is meaningless for most of it. It's like, okay, I kind of get this is how you'd calculate it, but like, what all's going on? When you can actually see the spectrum of the filter, and you can see its shape, you can see how much attenuation is there, where is it, what's the slope of the curve, then all of a sudden it's like, oh, that's the money shot. That's the meaningful information I was looking for. So that's why this sort of instrument to me is just so useful, because you can look, it's 10 instruments in one.
Yeah, it's the distinction that I'd like to make in a lot of my presentations, where it's the kind of the intuitive understanding of what's going on versus the scientific, do all the math, kind of science versus engineering, right? Like I prefer the let's build it and measure it and iterate until it works the way we want it to, versus getting stuck on all of the mathematical analysis and whatnot. They both have their place, but my preference is for the kind of the intuitive understanding. Let's look at it and measure it and iterate.
Well, and if you're really trying to understand something, this allows you to get past the abstraction and see a concrete example. And then if you want to have a true understanding of what's going on, like at an engineering level, then you can go back and figure out the math and, oh, that's, now it makes sense, right? Otherwise, it was just an abstract concept. So this makes it much easier to wrap your head around the application.
George,
what were you saying, Mike?
I have a real world example here because I used to fly a lot of model airplanes. And model airplanes, the way they communicate is send a series of pulses, pulse width modulated, that tell, and a lot of hams are like our seaplanes too. They tell it where in that string of pulses what's going on. And there's a couple of different sort of standards. And I was having a real hard time with something, and I ended up, and I don't know enough about it, but I knew if I could capture a picture of the waveform and send it to one of the designers, you go, oh, I'd see what the issue is exactly. And so while you may not understand all the stuff George went through, the ability to use a tool to see and get a visual to grab it, and maybe have somebody more technically inclined review it and go, a picture's worth 1,000 words. And this is where this, for the those of us that don't have the formal education or the experience that Mark and you have in your worlds, but to at least, they're good reason to have good test equipment, even if it's to have help.
Absolutely. And a lot of us don't do this stuff for a living, but, would like to have a deeper understanding of what's going on. Even if you don't, you don't need to know the physics of it. It's like, if you just understand what's the behavior, then you can start to debug stuff. I thought one other example that I want to show before we're done is just looking at audio out of a receiver. So, your favorite handy talkie that you've had for the last 10 years. I just plugged in a little breakout board into the speaker jack and routed that into the speaker output.
Actually, Rod has asked you to expand on what that breakout board is.
Oh, okay. So this is, I can't tell you how many times I'll sit here at the bench and I'll do something like take one of these little hooks and clip it onto a connector, and like, it'll stay on for as long as it takes to hook on the next thing, and then it flies off.
Yeah.
And so I just make little breakout boards. In fact, I was thinking for the workbench, I'm thinking about making a series of breakout boards because
heck yeah.
Remember I mentioned this earlier today? I had to do this exact step. I need to make a couple of these.
So all this is it's just a pigtail, and this is a 3 conductor. I want to do one with 4 conductor because that's very common too.
Yeah.
And so this set of you can see these are 8, like a 2x4 header, 3 of them. So this is the ground shield. These 8 pins. I don't really need 8 pins. I need like 2, but 8. These 8 pins are the ring, and these 8 pins are the tip. And since the tip often carries audio, I also added a little 0.1 microfarad capacitor and another 4-pin header. And so if you hook here, it's straight to the pin. If you hook here, it goes through the capacitor. So it DC isolates. So the speaker audio will go through the capacitor. That way I don't have to get rid of the DC offset. So anyway, it's just a little breakout board.
We're getting a lot of "shut up and take my money" in the chat room.
Well,
so I think we did find a potential ham radio workbench product.
So what I want to do, I made a, where'd it go? I made a note to myself earlier today about this. I want to do audio connector breakouts to headers and also to little screw terminals. I want to do it for audio connectors. I want to do it for RJ45 like Ethernet connectors. I want to do it for DC power and any other connectors that we use in ham radio in particular. So that way you have a little, a little herd of handy breakouts.
They're talking about all in a debugging kit.
Yes, exactly.
I want one now. A suite of handy tools.
Yes.
Yes. Take my money for all the breakout board set.
You know what the best thing about that project is, Mark? There's no firmware upgrades.
No firmware. Why do all of my project ideas have firmware?
Okay, so what I've got here is for the oscilloscope on the AD2, I've got the shield of the connector hooked up to the black wire, and I have the tip hooked up to the green wire, which is the scope input, and the ring is not going to anything. And so I'm just plugging that into my little Yaesu audio adapter. And so right now we don't see anything on the scope because the volume's down. So I'm just going to turn the volume up, and I should probably change my my range setting here.
And you want to set your sweep speed as well. You're sweeping too fast.
Yeah. Alrighty.
There you go.
So there's your typical unsquelched audio noise coming off the receiver. So I'm going to turn
noise.
on. Huh?
Hey, look, noise.
Now I'm going to turn on my signal, my RF signal generator, to hook up to this thing, and the signal generator has a big fan, and I don't know what this is going to sound like, but we're going to give it a try. It'll sound a lot like that.
Does your signal generator have tubes or something?
No, but it's a noisy thing.
So it's not an IFR.
No, it is an IF. It's an IFR 1600 in this case.
Oh.
Mike, you're making it through.
All right, so this is my stack of adapters to go to the signal generator. All right, fire in the hole. Here goes the SIGGEN. Let's see if it makes too much noise.
I hear the beeping, but I don't really hear the fan.
Okay, good. It takes a minute for the thing to boot up, so we'll let it boot up. While it's booting up, we could do this. We can come over here and say KJ6 VU Kilo Juliet 6 Victor Uniform. So this is how you impress the kids at Christmas when you want to show them your electronics lab. So they can actually
assuming you don't have a Jacob's ladder.
Yeah. Oh, guess what I got for Christmas?
A Jacob's
ladder?
ladder?
Get a Jacob's ladder?
I got a Tesla coil.
Oh, nice.
You know what the really funny thing was? Guess who else got a Tesla coil for Christmas?
Who else did?
Yeah.
I'm guessing Carol.
Mrs. KJ6VU guy.
Yeah.
So we gave each other. Neither one of us knew. We exchanged little Tesla coils.
You two are so perfect for each other.
Ain't it the truth? All right.
Can you go over to the spectrum analyzer?
It's still booting up.
No, on the waveforms.
Oh, yeah. What do you? So there's the audio.
Key up again. And I'm curious, do you have PL enabled on that one?
There is no PL. I can turn PL on.
I was thinking the same thing.
Yeah. Turn on PL if you can.
Yeah, PL's on. But the frequency is really low on the spectrum analyzer. Hang on.
Oh gosh, that's up in megahertz. Yeah.
Yeah. We want
to make it
change that.
Bring that down to like
8K.
4K. Enhance, zoom, enhance.
Oh, there we go. Let's bring this down to. Here's 0 to 20 kilohertz.
Can you go any more?
Oh yeah. Go as low as you want. Let's go. Here's 5 kilohertz. That's probably more useful.
Better.
That's good.
There you
yeah.
go.
Okay.
That's better.
Okay. Now I'm transmitting. There you can see the PL tone.
There it is. There it is. Right there.
That little peak down there is the PL tone.
Hello, 1, 2, 3, 4, 5. KJ6VU testing.
PL tone or CTCSS or
just to prove it.
Other terms?
Now I'm keying up with no PL tone.
Mm-hmm.
Yep. Yeah, PL. You can tell we're old Motorola people.
PL forever. Okay.
Yeah, cool. Thank you.
Now let me turn on the RF signal generator. Let me set it up.
Do your lights dim?
I got to turn on the generator.
Fetch 872 is asking which Tesla coil, if you can provide a link.
I don't recall if it's. Yeah, I'll have to put it in the link afterward. I don't recall off the top of my head.
Amazon?
Yes, Amazon.
Oh, well, that's got to be easy to find.
Yeah, well, there's several actually.
We're on it.
I'm going to look in Canada.
Oh, yeah, there are a lot.
Oh, look at those.
They're really cute.
These are not ridiculously expensive. There's some that are less than $100.
There's minis down to 20.
Yeah.
How have I not ordered one of these before?
Yeah, exactly.
What's wrong with you, Mike?
Like, I still want to get my analog device thing ordered, but my U.S. credit card's upstairs. And good thing I don't have it memorized.
Better do before they sell out.
That's right.
Yeah. Let's see if Rod wants one.
Combined shipping.
Well, George is doing that. Canadians now have the advantage of taking, cross-border entry points, right, where it's free shipping to nearby, and then they carry it over.
Yeah.
Okay, so this is what I was going to try to show. So right now the receiver's turned on and the signal generator's turned on, but the signal generator is generating a signal at minus 137 dBm. So minus 137 dBm is basically like no signal. Okay, so I'm going to crank up the signal, and you can watch the noise as the signal level goes up. You can see how the noise goes down. So this is essentially no signal. This is minus 120 dBm. So you can see how it's much more quieting. So the white noise has gone down quite a bit. Too bad you can't hear it. If you heard it, it would go from nothing but white noise to some white noise. And you can see some popping in there, what you'd call popcorn, typically. If I go down, let's say, to a minus 100 dBm signal, it's pretty much a full quieting signal at that point. So when you're measuring like receiver performance, like an FM receiver, you'll often see a measurement like this receiver is minus 120 dBm for 12 dB signal to noise or something like that. What they're really talking about is how much of it is signal and how much of it is noise at that certain RF signal level. And so you'd use a service monitor like this to be able to do that. So I'm just attenuating it more. Or
What's
I can go
causing that
back
popcorn?
That's a good question. I don't really know what
Tesla
causes
coil.
that. It's that's a great question. It's like there's my guess is that the noise is random, and there's probably occasionally some amount of random noise that occurs at the same spot. I'm guessing. I don't know.
Yeah.
And you get a little bit higher amplitude spikes, and then the higher amplitude spikes, as I attenuate more and more, turns to noise.
Dominate.
Now, what I can also do.
Hold on for a second, George. Just for everybody else, for the two tests that George is talking about, this is how they do receiver performance, and the two of them are 20 dB quieting. Is it 20 or 12 dB quieting? Was one way, is the one I grew up with, and the other one's called a SINAD test, which really just says exactly what he just visualized, which was probably the first time in 100 years I've seen it visualized and not on an analog meter.
So
I actually just took Secret Squirrel over to a friend's with a service monitor to have that measured, and
so it's a receiver.
It does have a receiver in it, yes. It wasn't great, and so I had to redesign some things, which is why I'm running a little behind on Secret Squirrel at this point.
So here's something else that's kind of useful for let's say you're doing like receiver testing. So right now I'm generating an RF signal at minus 93 dBm, which is plenty of signal to quiet the receiver. So if you're listening to this on a speaker, you would hear nothing, right? It would be a dead carrier. There's an audio signal generator built into the service monitor. So I just turned it on. I set it for 1 kilohertz, and currently the deviation of that is 0, which means you're not going to see anything. So I'm slowly increasing the deviation of that 100 kilohertz modulated tone, and you can see the audio amplitude going up, coming out of the speaker.
You said 100 kilohertz modulated tone. It's 1 kilohertz.
No,
right?
it's one. I misspoke. It's 1 kilohertz. Tone, and so I'm generating more and more and more higher deviation, and see what's starting to happen.
It's flat topping.
So what's the difference between here and here? To make it a little bit more obvious, what I'm going to do is I'm going to bring the signal down, and I'm going to change the sweep there. Hang on a sec. I'm going to change this. Oh, that's the offset. Okay, so this is a beautiful sine wave coming out of the service monitor. I'm going to increase the amplitude, the deviation essentially, on the FM carrier of that 1 kilohertz tone.
Ew.
See this? You know what that is? That is called flat topping, also known as distortion. So this is a way you can use your oscilloscope to see what's going on in your audio. So let's say you listen to someone talking, and there's a bunch of noise, and maybe it's because they're far away. Well, then they get really close and they're talking, and then maybe when they're quiet, the audio sounds good, but when they're talking really loudly, they get distorted. You can see that distortion in the oscilloscope. And so here I've driven the deviation of the transmitter. Now I'm at 7 kilohertz of deviation. The modern radios, the FM radios we use, are 5 kilohertz radios, meaning that full deviation is 5 kilohertz, and anything more than 5 kilohertz will be clipped. So what you're seeing here is the filter inside the handy talkie is clipping the signal when the amplitude goes above 5 kilohertz. And what you would hear is distortion. You would hear that sounding raspy. You would understand what they're saying, but it would sound very raspy because that beautiful sine wave is now clipped, and you're getting these harsh edges and this flat topping action. And if I keep going more and more, like here's 12 kilohertz of deviation, it's like pretty massively clipped.
Yeah.
So it'll sound just horrible. So my point behind all this is that you could use a scope just to start debugging common radio problems like, gee, your audio sounds crummy. Is it because your signal level is low? Or is it because you're overdriving your transmitter? Or is it because I'm off frequency? Or, what's the deal? If actually off frequency is an interesting one. So here's a case where I'm putting in 3.5 kilohertz of deviation in a 5 kilohertz passband. That should sound beautiful. And so what you're seeing here is a beautiful sine wave, right? That's a beautiful sine wave if there ever was one. Now, I'm going to change the frequency on my handy talkie and go 5 kilohertz off channel. So I'm now on 146.505. See what happens when I change frequency? You see a little bit of distortion in that otherwise beautiful sine wave. So this is why, like, when the other station is off frequency and they start to sound kind of fuzzy, they're still intelligible, but it's starting to get distorted. At 10 kilohertz off frequency, there's still audio coming through, so I can hear the modulation, but it is highly attenuated and very distorted. And then 15 kilohertz off, they've fallen out of the passband of the receiver, and I just don't see them at all. So 15 kilohertz off, 10 kilohertz off, 5 kilohertz off, right on frequency. So, you could do little things like that to start to debug, or maybe you think it's your radio. Maybe it's the audio amp is bad. If that's the case, you look at the speaker, oh man, the audio is all distorted. If you follow the chain before the speaker amplifier, if the audio looks beautifully clean, then you got a problem with your audio amplifier. If it looks distorted there, it's something further up the chain.
So a couple questions. One statement. Be careful with looking at distortion on a human voice. You probably won't see it. The human voice is not as clean and pretty as a sine wave is. You need something that's clean and pretty to be able to tell that it's distorting. Yeah. At least with moderate distortion. Once you get into extreme distortion, then you'll be able to see it flat topping.
Yeah, really, that's right. Extreme, just you can see it. You'll see on voice peaks. Actually, maybe we could.
But before you go away from this, I want to try something else out.
Oh no, I just shut off this.
You shut it off?
Yeah, go ahead. Let it warm up.
Now it's going to boot up again. I was going to have you change the frequency in the other direction because it kind of skewed the sine wave, and I wanted to see whether it would skew the other direction because you're coming in the other side of the passband.
Yeah, it's booting up.
Now we're waiting 10 more minutes for this thing to boot.
Let's see. Let's go to. All right, we're up. Let's go to FM deviation. Okay, here we are back. There's 3.5 kilohertz of dev with a 1 kilohertz tone.
So go 5 kilohertz down this time.
That's down.
Yep.
That's up. So exactly what you thought.
Yeah, it's skewing the other direction. It's kind of neat.
And by the way, you can tell if someone's off frequency, which direction they're off, because if they're kind of distorted, if you look at it on the scope and you swizzle your frequency up and down, if they look better 5 kilohertz high, they're probably 2 or 3 kilohertz high. So
yeah,
it's a good old way to actually check it out. So ain't that fun?
Okay, cool. Thank you.
Yeah. All right. So I'm going to shut off the service monitor. So anyway,
I gotta get me one of those.
That's kind of the last thing I was going to show on the demonstration here. Do we have any more questions in the chat?
No. Muted. No, we're good.
Yeah.
Cool. All right. Well, we learned one thing today. We need to build some breakout boards.
Yes.
I like Marty said in the chat, I can't believe I didn't think of this about 37 years ago.
Yeah, no kidding. Well, and we spent the last 37 years hooking stuff up and having it pop off, and
Well, my next idea, George, was to make those little clips we use just a little bit bigger to hold on to a
3.5 millimeters,
3.5 millimeter thing. By the way, I was sitting on this. So your Agilent and log discovery 2 pretty much and more replaces one of these.
Yeah.
Yep.
The funny thing is, Mike, which one is that you have there?
This is given to me by Kevin V3KH. This is the TDS 210.
By who?
What brand?
Tektronix.
Tektronix. Okay.
So I have here on
60 meg.
That's a very nice scope.
Yeah.
The scope I normally use is a Rigel. It's got the big, the big display, whatever, 7-inch display. I think I use my 82 probably 10-1 over the Rigel, and the reason is that I just find the software so convenient. Oh, actually, one last thing before
I have one of those, George, too. It's sitting over my other workbench.
Oh, the Rigel.
The Rigel. Yep.
I was going to show one last little thing here. Let's go back to the palette. I wanted to show you the static I/O panel, which I thought was actually pretty useful.
Yourself. George, you'll need to explode yourself.
Yeah. Okay, I'm going to turn off the receiver there. Let me just switch the view. Alrighty. So what you see here on the left-hand side, there's a digital I/O, 0 through 7 and 8 through 15. So there's 16 digital I/O. There's fancy ways to use this, like monitor a I2C bus and show the commands that are being decoded and all that stuff, which is useful. But for most of us, a lot of times you just want something really basic. So you can set each of these individual things here to have a different personality. So you can make it an input or an output. So I can make it an LED, or I can make it a button, or I can make it a switch. And there's even different flavors of buttons and switches, which is pretty cool. So like, I know what, I can do a quick rewire here. I'm going to take the bit 15 and bit 7, and I'm going to cross connect them together. So I'm going to make this one an LED. I'm going to make this one
0 and 8.
Oh, I'm in 0 and 8. Let me
15 and 7.
All right, there we go.
Oh, that works too.
Okay, so 8 is an LED, and 0, I'm going to make a switch, and I'm going to make it a what? How about a
you want
push-pull switch?
Yeah.
So you can see how it becomes a little toggle switch here. So I can set it to a logic state 1, which turns on the LED, or I can set it to logic 0, which turns off the LED. And this is just wiring those 2 pins, just jumpering those 2 pins together. So you can see here, it's just these 2 pins now are jumpered across. So that way you could, for example, take the digital output and hook that up to a control pin on an integrated circuit. And maybe that integrated circuit is going to do some function when that pin goes high or goes low. And you can now control that pin from your display. Or you can have an output. Let's say, like I was doing a DTMF decoder project where I had an 8870 DTMF decoder chip. And the way the chip works is you have audio going into it. And when it decodes a DTMF signal, one of 4 pins, or rather the four output pins, will give you a value between 0 and 15, because there's 16 buttons on the DTMF pad, right? So you'll get, a different bit pattern of those 4 pins, depending on which DTMF tone is being decoded. There's a 5th pin, which is called a data valid pin. So when there's a successful decode of that tone and that 4 bits are set, you'll get the 5th one going low to say what you're reading is actually legitimately there, as opposed to just a random set of 4 values. My point is, you take those 5 pins right off the DTMF decoder chip, hook them up to these 5 LEDs, and now I don't have to solder 5 LEDs on it. I can just hook it up to this thing and I can actually see it. So I could generate the tone with the tone generator, as it turns out, because you can generate complex tones, and I could see it decoding on the LEDs. So when you're designing and debugging subcircuits, it's also really handy to use this static I/O thing just to control and observe digital signals. And and then you can also automate it. So with the scripting language, you can actually go in and say, okay, set this high, wait this amount of time, set this low, wait this time, take this measurement, etc. And you can do all that kind of automation stuff if you really want to. So anyway, I thought that was one last little thing. And there's other stuff we haven't even touched on yet, but I mean, that's like the bulk of the stuff that I tend to use this for.
Yeah, I agree. I think the oscope, the signal generator, and digital logic analyzer kind of stuff is the majority of what us hams and makers would use in our workbench kind of environment. I think that's, and then once you are used to using it in those ways, then you can start diving into some of the more detailed modes and analysis modes, and serial debugging and stuff like that.
Right.
But
yeah, exactly.
This is fantastic.
Or even like this, I use the spectrum analyzer, the network analyzer. So let me show you one complicated project.
Let me take an opportunity, chat room, if you've got any questions for us, now's the time, because it sounds like we're going to be wrapping up before too long. So please poke any questions you have into the chat room.
So this is a project that I've worked on recently. So this is a board out of the repeater controller that I designed. So you can see there's a whole bunch of surface mount parts. This is the whole analog audio chain. So in the middle of this thing is a PL filter. And so the way the PL filter works is you have your FM audio signal after it's demodulated come in, it's buffered, and then it goes into a PL filter, and you can jumper it in or out of the circuit. And the PL filter basically takes the PL audio out of the audio chain. So normally you want 0 to about 4 kilohertz of audio, and you want it pretty flat once it's in the circuit. And the PL will be below 230 hertz. So I built a filter, actually a pretty steep 6-pole filter, 6 or 8 pole, I forget, that will roll off everything below about 150 hertz. So about 3/4 of the actual PL tones. You can't use a higher PL tone with it. That way we have better fidelity. So anyway, it rolls off the bottom PL tone frequencies. So I use the network analyzer to look at not only the spectrum to see, how effective is the PL filter, how flat is it, is there any ripple in it? In other words, does it vary? In theory, you want your filter to be, like lets nothing through and then it lets everything through if it's a low pass filter, right? But there's always, as you cascade multiple filter elements to get more steeper skirt, you tend to also have to look at the ripple to see if, is it flat or not? Anyway, so not only can you see that with the network analyzer, you can also see the phase delay, what they call group delay, the phase difference over frequency. So you can see if there's any shifting of phase and if that's going to accumulate and become a problem downstream. So all that stuff you could do with the 82. I mean, you can probably, for most hams, you kind of like, you'll never need another piece of test equipment. Mark, it sounds like we sell these things.
I know, right? Yeah, at audio level, yes, it will absolutely do anything you need it to do. It's when you start getting up into RF levels, like if you're trying to sweep IF filters, if you've got a 455 kilohertz IF, then yeah, you could probably do that on this.
Right.
You'll want to use the good scope probes, not just the little wire leads. But if you're talking, into the 10.7 megahertz IF or 15 megahertz IF or whatever, those you're going to need an RF device for. This won't do that.
That's right.
But it's so much of what we do is at audio, and this thing works great in audio.
Yeah, audio or DC
digital
logic, even like a lot of logic. A lot of times we've talked about this over and over on the show. We talked about scopes. People say, well, how fast a scope do I need? Do I need a 50 meg scope or 100 meg scope or faster? And the answer is, like, you will probably never need a scope faster than 10 megahertz.
Most likely.
Because probably 99.9% of the time, you're either looking at audio or some low frequency RF signal or some digital signal that's probably so slow that any oscilloscope will resolve it. Almost any of these are good enough, unless you have a very special purpose need. Then of course, sure. If you need to look at a high speed, a gigabit digital signal, yeah, then you need a very expensive fast scope. But most of us aren't doing that, so
No.
it doesn't really matter.
If you're asking the question, chances are you don't need anything more than 10 megahertz. Yeah.
Well, the
Yeah.
other nice thing too about a 10 meg scope is 10 meg scopes are the ones that people give away for free.
That's right.
So I
That's how I got
have,
this one.
I mean, I think I gave away all my analog scopes. I don't even have any anymore because they were
Yeah,
about
one of them
40
sitting
times
right
the
there.
size. Thank you.
I think I picked it up at Baycon 2019.
Yeah, why do you think we used to have Baycon? Baycon was the excuse for me to clean out the garage.
Get crap out of George's Garage Con.
Yeah, exactly.
That's how stuff ended up in my mailbox.
Well, I have seen several people in the chat room saying, okay, guys, I bought an AD2. So, yeah, we may want to contact our friends over at Digilant and see how many sales they got over the Christmas break.
So
Yeah.
there were some people asking in the chat. I posted the link a couple of times. You have to go order the Ham Radio Workbench bundle. It says exactly that.
Yeah.
And then it's Ham Radio Workbench 2021. I had used all lowercase, and that works for $126 off. And I think it's free shipping in the US. And in Canada, it was reasonable FedEx priority shipping to Canada. Of course, for us Canadians, we'll still have to pay HST when it comes across the border and a bit of duty, but you get it.
So I guess the other question that we have for those of you still watching the stream, is
Shoveling
this
your
useful? What is useful about? We tried a bunch of things in this stream. We tried showing a piece of equipment. We tried a little bit of circuit theory. We tried a little bit of other like gadgetry. What would be useful for other live streams? Because one of the things that we've been talking about for the last 6 months is that we'd like to do more of this sort of thing. Not to do this in lieu of doing the podcast, but doing it as a supplement to it or on topics for which we may not do an episode, but would lend themselves well to showing something on the bench. So we'd love to get feedback on ideas, either for topics or just the nature of what we're trying to do. What sort of thing would be useful?
Yeah.
I think it's a great idea.
I do too. I love these.
It's a lot of fun too. Frankly, it gives us an excuse to build something, even trivial though it might be, like this little test circuit. But having something like this around is handy for actual real projects. And by the way, when we're talking about the connector breakout board thing, another idea is little circuits like this that would go along with learning how to use your, whether it's an 82 or something else, learning how to use your scope or SIGGEN could be really useful. I mean, you don't really need a board with an op amp. I mean, although for like plugging in components and seeing how they affect the circuit and all that could be very useful.
Yeah. Looks like we got a couple of Raker suggests a video on how to tune cavities. I assume he means duplexers for repeaters. Love seeing the demo of the circuit interacting with the equipment. And let's see here. I think it was very useful. This is a great concept. Maybe using that service monitor. Oh, that would be a good one. So an episode on how to use a service monitor and what you can accomplish with them.
Yeah. Yeah, that's a good idea.
That's a good one.
Yeah.
Yeah.
Actually, I think one thing that's also useful, maybe this is a topic for the podcast, is to talk about not only what is a service monitor, why would you want a service monitor as opposed to individual pieces of test equipment, like a spectrum analyzer or a sign adder or there's a bunch watt meter, because essentially a service monitor is a bunch of stuff in a box as opposed to individual instruments. That's more portable in the sense that one could theoretically lift
luggable.
Because they're generally not that. They're portable by young field service technicians.
Yeah, but the ones we're getting today that are making a damage are like an IFR 1200S is you can probably buy for $1,000, and it's anything we'd ever want to use, because the new ones are being replaced by battery powered and lighter, and but they're out there and they're still phenomenal tools to have. You know,
Yeah.
and you can usually get them at Dayton. Of course, we haven't had a Dayton for a while, but
There, as usual, there's a lot of stuff on eBay, and I've had pretty good luck buying that kind of stuff on eBay as well. There's also specifically for service monitors, there's a few places that specialize in them. Now, a lot of these service monitors that we get, you know, some are 10, 15 years old, and a lot of them are 30 plus years old. This 1600 that I was just using here, that's in like immaculate condition. This is probably a 30-year-old piece of equipment, but I would never have bought it when it was new, but used, you know, they're great.
Fetch 872 had a question, and George can override me on this, and I would probably say for what we do, almost never. And the question was,
repeat the question.
Calibrated?
Yeah,
and you know, they'll drift a little bit in and out of accuracy. They may not be commercially accurate anymore, but well within anything we would want to do.
Oh, is he asking, should they be commercially calibrated?
Yes.
Or how often do they need to be calibrated?
You know, you can actually, once a device is, any of these service monitors, if they're calibrated and you leave them on your bench, odds are pretty good they'll never need to be calibrated again. So if you buy one that's been calibrated, you probably never need to do it. And frankly, I mean, to your point, Mike, even if it was out of cal by a little bit, it's probably not enough to make a difference.
If you buy one used, if you buy one at a Hamvention or Dayton, you do want to put it on the bench and play a couple of things through it to make sure what you get from it seems about right. Maybe in terms of RF power, is my handheld putting out roughly 5 watts? Well, the problem is you finally grab 3 or 4 meters, you're then going to go, which one's actually right? But and start comparing things and certainly receiving sensitivity.
I tell you what your calibration is probably not your biggest problem. The biggest problem with a field piece of test equipment like a service monitor is the most likely things that have gone wrong is if it's an old one and has a CRT, that's probably the biggest failure point in the whole circuit, because those CRTs are 35 years old and they weren't great when they were new. So they're like, you know, newer service monitors will have plasma displays. Even that's old by today's standards, but that would be better. So CRTs tend to go. Power supplies sometimes will go. You could find, the batteries, absolutely. Assume the battery is no good, and assume you're probably not going to replace it because they're too expensive. But you'll probably run it on 120 volts
AC power anyway.
The other thing is the front end, the receiver in them. The older models did not even have front end protection circuits. Most of them, probably 9 out of 10, you'll find if they have a built-in dummy load, then there's a built-in protection circuit that samples the RF and attenuates it before it gets to the receiver. Unless there's a jack on the thing that it's the direct receiver input, in which case someone could have transmitted into it. That's been known to happen. This is one of those times where this is not a joke. I didn't actually do that. But I've seen it happen, and people have to replace the front end FET in the service monitor. So I mean that does fail if somebody blew it up. But aside from that, you know, unless like a lot of these things have many circuit boards and a motherboard inside the box. You know, if something got unseated or wiggled, or or you had a capacitor fail. I mean, those things could happen, but these things tend to be pretty well built. So calibration is probably not your biggest problem. It's probably one of those other things.
I had a 1200S that got the ROM boot up error, and it turned out that the onboard 3-volt battery had died, and I took it apart, and it was 1.5 volt or 3 anyway. I just found the battery, tossed it, brought a couple of leads out to a double A battery holder at 3 volts, put a couple of lithiums in it, put it back together, wedged it all back together with a bit of foam tape, and that was 11 years ago.
Yeah. I had a 1200S where there's a BNC connector on it that was bent, and that was the reason the guy got rid of it. I just had to replace the BNC connector, and it was all fine. Go ahead, Mark.
Nice. Donald Gover has a suggestion. He says, how about we take the breakout boards and use that? Did we lose George? Oh, no. Okay. Take the breakout board idea and use that as a live stream to demonstrate how to create a circuit board on either KiCad or Eagle And so, because since the breakout boards are super simple, we don't have to worry about, oh, well, this op amp we're going to design this way. We could just concentrate on the schematic and board layout program and not have to worry too much about the circuit itself.
That's a capital idea, because I know nothing about how to use Eagle, and that would be a great idea. I'd love to do it.
Well, I have two comments. First of all, hi, Donald. It's great to virtually see you. We actually did do a live stream on doing circuit board design with Eagle. So it's on the YouTube channel. So if you look at the HRWB YouTube channel, I posted the video of designing a little circuit board from scratch. So there's one there. And if it's just, pick a random simple circuit, design it from scratch to make the board, that's already there. But maybe there's some other thing that we should do that would be different than that, and love to know what that is. So take a look at what's there and see what you'd recommend in addition to that, and let us know.
So George, in your example, do you say, okay, does it include saying going to DigiKey to source the jack that's going to be soldered on the board, and then how you work it in?
I think so. I think I did for what's on there is not a breakout board. What's on there is
I know that. I meant
it's just a little voltage regulator. It's essentially a 7805 with two capacitors. And I think we did go to DigiKey and do the hunt for the part, but okay. I don't remember for sure. It's been a year since I did the video.
All right.
But actually, hunting for parts that's a whole interesting topic by itself, Mike.
And it's changed over the last year or two.
Yeah. So the funny thing about hunting for parts is, if you need a very specific, like an integrated circuit, that is really easy to find. If you want to buy something like very generic, like a
10K resistor,
a 10K resistor, there's like a million different part numbers for a 10K resistor, and waiting, it's like there's too many to choose from.
Yeah.
So that's the biggest headache.
And Mark, you're okay in both places, by the way.
What do you mean?
Your video.
Okay in both places. Yeah, it locks up every once in a while, apparently.
You're streaming fine in both places. So.
Well, we're kind of coming up on the 2 hour. We'd planned to do this for 2 hours, and I think we're kind of just about there. So unless there's any more questions in the chat, do you guys have anything else before we wrap up?
No, I wanted it to be an hour. You said 2. You were right.
Well, normally when I say 2, it's 4. So.
Yeah. The fact that we're wrapping up before 2 hours, I think, is a win. Yeah.
I was thinking miracle, but yeah.
I think this was good. We're getting a lot of positive feedback from the folks that are still in the chat, although that may be a little bit of selection bias. But I like the format of this, of when we have something that we want to go into more detail on, or something that's very visual, like using waveforms is. Like, trying to do this over an audio-only podcast is just maddening. I don't think this would work out at all. Yeah. But doing this in this kind of format, I think, is great. Don't worry, we're not getting rid of the audio-only podcast. That is the primary media format that we're doing here. This is definitely just an adjunct add-on to that.
And I think when we do the video things, the reason why, at least for me, this is reasonable to do is because we're not trying to edit this down into a 5-minute snappy video. Well, we're just letting it roll as a live stream because it doesn't take any editing work on our part. If we had to actually take 2 hours and turn it into 10 minutes of useful content, we wouldn't do it. No. So that's probably why we'll stick to this.
Yeah. So we had somebody, Fred Hewells, asks where the 82 bundle can be purchased at. It sounds like Digilant.com, and then search for the Ham Radio Workbench bundle, and then use the offer code Ham Radio Workbench Podcast 2021. And I think we found out that capitalization does not matter on that code, and you'll get about $125 off of the bundle. The bundle comes with the Analog Discovery 2 itself, the breakout board, and I believe a bunch of the little fly wires and some scope probes, if I remember correctly.
Let's just look it up while we're at it.
Well, there you go.
I did put the link in there, George. If you could, I don't see it. Didn't make it back into. I guess the links don't get posted. You want to full screen yourself? I have it up here if you want to just give me.
Greg S. Go ahead. Sorry.
Do you have the
Let me just,
Digilent website handy
I do.
there?
Just a second. Yep.
Yeah, go ahead. Just go ahead and bring it up then, and we'll.
So Greg SA9089 tells me that the AD2 will do a 10.7 megahertz IF filter. He used it on his waveform. You do have to go into waveforms and say, yeah, I know it's out of spec. Do it anyway. And it'll do it, apparently. It's not too far off. It's probably not going to give you an accurate number, but again, if all you're doing is measuring relative distance, or differences, it'll probably, this many dB down is probably pretty accurate.
Yeah, remember with the spec on a scope, it's not like it stops at 10. I mean, it'll work with 20 megahertz. What happens is there's a roll-off. And the measure, like you're saying, Mark, the accuracy of the measurement is unpredictably bad. But if you're just tuning for maximum signal, that'll work fine. You just don't know what the level actually is.
Exactly.
And George, you have to present my screen.
Yeah, let me make you the main. There you go.
Oh, I know. You still have to present my screen.
Oh, I have to present your screen. Okay. How do I do that?
Just the 3 dots. It's in the blue or the.
Technology is hard. Whoever thought it was a good idea to teach sand to think?
I have no idea how to do that.
Oh, so apologize to everybody else. To see in the bottom, you should see me in
Oh,
the
that
waiting
one.
area.
I didn't see that one.
There you go.
All right.
Now make it full. Not me. You.
Almost.
Not
Oh, I
you.
almost hit remove. I just have to switch to you. This is
Computers
complicated.
are hard.
There we go. And I'll just blow this up a bit. So this is what it looks like when you find it. Let me explode it a little bit. And it's the Ham Radio Workbench bundle, and the link is digilent.com. And I did paste it in anyway, /shop, and it doesn't show it, /Ham Radio Workbench bundle, and there are dashes between everything. But if you poke around, you'll find it under right here under test and measurement bundle products. So if you click there, and you'll see the Ham Radio Workbench bundle. And you get $126 off, I think, if you go into add to cart and shop, and then there'll be a coupon.
Yeah, it winds up being pretty close to $300. It's like $320 when it's all said and done.
That's about 25% off. That ain't nothing. When
Yeah.
a lot of discounts are like 5% off or 10% off. Like, yeah, okay.
It's pretty significant. The Digilent guys are great. I mean, they were super supportive of the ham radio community. They're very maker centric. So they were really very happy to do this. And just to emphasize, we don't make a nickel on this. We don't get, they're not an advertiser. They don't give us a commission. We don't get any jack nothing for doing this.
We just like the product.
We just like the product.
Yeah.
All right. I guess that'll be it then. Any last words from you guys before we wrap up?
Well, if you're watching this live, have a very happy New Year, and maybe you're off this week, and you're good. Get on the air. Whatever that is for you, get on the air.
Yeah, we have a show coming up. Let's see, on Tuesday, the next show drops. We recorded it so long ago, I can't remember what it was.
I think it was Kyle.
Yeah, actually it was Kyle. So this is Kyle AA0Z, and he's going to be talking about his build project that was building a network, a computer network in the field for contesting, like Field Day.
Network on a stick.
What's that?
Network on a stick.
Network on a stick. Yeah, it was really a fun one, because there's a whole nother project that he's working on that's really exciting, and you'll have to check it out on the show. We talked about his other project in the What's on Your Workbench segment. So I think we spent a whole hour on that.
Was that the big screen thing?
Yeah,
that's pretty cool.
Yeah, very cool. So check it out. Show goes out on Tuesday, and then after that we have Doug Millar, who's going to come on and talk about coax, cables, and connectors. And we'll get into some of the specifics of what makes for a good coax or bad coax, and connectors, and some do's and don'ts, which is a whole rat hole on it by its own.
Everyone's got opinions.
Yeah, and we'll even have some facts thrown in just to make it interesting.
What?
And then let's see what's up after that. We've got a bunch of other stuff. I can't remember all the other topics. And we have some announcements coming up. We have some exciting announcements of some things that we'll be doing in 22 and some other stuff. So next few episodes should be pretty interesting. So thanks everybody for watching the live stream. Love to get your comments, and just comment on the feedback page on the Ham Radio Workbench website. That would be great. We'll see all those, and get your friends and family to subscribe to this YouTube channel, and we'll do more of this stuff.
Yeah.
So thanks a lot. Thanks for watching.
Sounds
Thanks, Mike.
great.
Thanks,
Be good
Mark.
humans, everyone. Thanks, George.
73.
Thanks for you guys.